Welcome back everyone. My name is Sagar and we are back here with another video. So today is day 185 of our POTD series and this question name is minimize number of students to be removed, and this is given a medium level question. So we can consider it as a medium level because it is a very interesting question. So first of all, n students of different sides are standing in an assembly. So there is a assembly going on and there are total of n students, right? And after that the height of students are represented by an array. So we are given an array of size n and that represents the height of every student. And the problem is that if a student has less or equal height than the student standing in front of him, then he or she cannot see the assembly. So that means there is our first student, then suppose there is second student. So that student can see the assembly, right? But suppose there is some student that is smaller. So assembly is going on here and this student can see the assembly. This also can see the assembly because this student have a height greater than this previous student, right? And suppose there is some student that have a smaller height than the student that is standing in front of him. So obviously this student cannot see assembly because this student have a greater height. So what can we do now? So this student should be removed, right? So the problem is that if a student has less or equal height than the student standing in front of him, then he cannot see the assembly. So obviously this student cannot see the assembly, and we have to find the minimum number of students to be removed such that the maximum possible number of students can see the assembly. So there are two steps. So there are two things that we have to do in this question. That is minimize number of students to be removed, and the second thing is maximum possible number of students can see the assembly. So we have to maximize the thing that mostly maximum number of students should be present in the assembly, right? So suppose there are n students right here. So suppose this student have a greater height, and let me just clear it. So suppose this is here a one student and there is the second and there is third. So what can we say? How many number of maximum students can be there in assembly? So first of all, this student should be there because this is the smallest one, and we can add this student. But this student is gonna make a problem for this student, है ना? So what can we do? Either we can remove it or we can just add this one. So either we can add this or this. So there are two choices for us now. So first of all, we are adding this student, then either this will be added or this will be added. So there are two choices for us, right? And after that, we should add this student in both of the cases because this student have height greater than both of them. So after that, this student. So this student cannot see assembly. So we should remove this. Even if we are removing this taller student, then even then after removing this student, he still cannot see the assembly. So we should remove this student which have a very smaller height, right? So we will just remove this student, and either we can remove this or this. So after removing any of them, the maximum number of possible student in our assembly is 3. So if we are removing this student, then the maximum possible is 3. And if even if we are removing this student, then still the answer is 3. So the maximum answer, the maximum students in our assembly is 3. But what we have to return? We have to find the minimum number of students to be removed. So we have to return the minimum number of students that we remove from our assembly. And that is there 1, 2. So what can we say now? We have to return total number of students minus the maximum students that are present in our assembly with increasing height, right? So the total number of students are 5, and we can see the maximum number of students that will be present in our assembly will be 3 that have their increasing height. So first of all, smallest student, then height will be increased, and then again increased. So there are 3 students, maximum 3 students can be present in our assembly. So the answer will be 2. That means we have to remove minimum number of 2 students to satisfy this condition. That is maximum possible number of students can see the assembly. So our answer will be 2. And suppose for our this example, so we will just see this example and then we will think how can we approach this problem. So first of all 9, then 1. So this is our height, then 1, then 2, 3, and 1, 5. 1 and 5. So we have to find the maximum length, right? We have to find the maximum number of students that should be present in our assembly that have their increasing length, right? You can see this is in increasing order. First smallest student, then height is increased, then increase. So this is in increasing order, or we can see sorting order. So we can see 1, 2, 3. This is increasing, and if we remove this student and add this, so this will be also increasing. So there are maximum of 4 number of students that will be present in our assembly that have increasing height, right? So what can we say? How can we solve this problem? So first of all, we have to remove this and this. So we have to remove 2 students. and the answer will be 2. So maximum number of students is 5, and we can see the maximum increasing subsequence. This is a subsequence, right? Because we are not including these consecutive elements. So the maximum increasing subsequence, or we can say LIS, longest increasing subsequence. So this is a very simple problem of our simple longest increasing subsequence. So we have to find the longest, that is, you can see we have to find the maximum number of students and that have their increasing height, so that everyone can see the assembly. So longest increasing subsequence, because we can remove the student from in between. So here it is 4. Sorry, the total number of elements are 6 here. So 6 minus 4 is equal to 2. And that is it. So this is a native problem from our longest increasing subsequence. So how can we do this problem? So this is a very simple method of our dynamic programming, and we can just do this question in a very easy way using our n square time complexity. But that won't work because our constraints are 10 to the power 5. But still we have to do that thing. We will just see that approach so that you will get comfortable with this LIS problem, right? So how to do that? So let us just see how can we solve that problem in our n square time complexity. Then we can see for optimizing this, right? So first of all, how we can do this in our n square time complexity. So first of all, this is what we have to do in this approach. So what is LIC problem? Longest increasing subsequence. We have to find the maximum increasing subsequence from our whole array. That means first of all, what we will do? We will find what is the longest increasing subsequence up to this point. So after that, what is the longest increasing subsequence up to this point after including this value, right? So first of all, we will include 9. So what is the maximum longest increasing subsequence from this point to this point? So we will have two values that define our range. So we can see if we have only one element, then the longest increasing subsequence will be 1, and we can just say the exact same thing for our every value. So if we have only one value in our range, so from this point to this point, then there is only one value. So the longest increasing subsequence is 1 when we have only one element in our range, and we can just do the same thing for every value. But after that what we can do? So after this, what we will say, first we will start from this point and we will check from all other points, right? So if we have some value here, then we will check from this range. So we will check this range, and then this 1 to 3 range, then this 2 3 range, and then this single 3. So we don't have to check this single 3 because we already have that answer, right? So first of all, what we can do, we will start from this one, that from 1 and up to all other subsequences we have. So what we will do, first we will check from 1 to 9, so this range. So what can we check? First we have to check either this value, either this one is greater than the previous value, that is our ith value. So suppose this is our ith value, and we can say this is our jth value. So what we can say, if this value is greater, so we can say I is next to our j, so our j is before I. So this ith value should be greater than our jth value, so that this will be an increasing subsequence, right? So if our ith value is greater than our jth value, then we will add the ith value's maximum size. So but in this case this is not possible because ith value is smaller. So we will just say as it is. And after that our I will be increased. So our I will be here at 2. And after that we will check every subsequence. First of all this one, and after that this one too, right? So first of all we will check this one from 9 to 2. So is our 2 is greater than 9? No, our 2 is not greater than 9. So we will just move ahead. So we will be here at 1. So we are now checking this subsequence, the maximum longest increasing subsequence in this range. So what we have to do now? So first of all, we will check either this value, this ith value is greater than this jth value, right? You can see here our 2 is greater than our 1. So that means we have to find our longest increasing subsequence, and this is satisfying our increasing value. So what can we do now? We will just get the maximum length of this range, that is from ith value. So what is the maximum length from this range? That is 1, and we will just add 1 because this is 1, because this value is 1 because of this subsequence, and we have to add one value to this. So what is this answer? 1, and we will just add 1 because this is also including in the previous range, in the previous subsequence. So I hope now you're getting this. And after that we will just add that value, this 1 plus 1, in our 2th value, that is our ith value. So 2, that means this value, that is up to this 2th point, up to this 2th value, we will have maximum longest increasing subsequence value equal to 2. So we are just storing that in our DP. And after that, let me just elaborate it more. And after that, we will move up to 3. So I will be here, and we have to check all the values from here, here, and here. We have to check all the subsequences. So I will be here. Okay, let me just remove this. So after that, we will check with 9. Is 3 is greater than 9? No, 3 is not greater. So we will check with 1. Is 3 is greater than 1? Yes, 3 is greater than 1. So what we will do? First, we will check. So j is here. So j's value is smaller and is value is greater. And after that, what we have to check? We also have to check one more condition, that is this answer will add plus 1, and this new answer will be greater than the current answer of our 2s value or for our 3s value. So is 1 plus 1, that is the previous answer of this value, that means previous value. So what is the answer? What is our previous value? What is the previous longest increasing subsequence for our jth value? That is 1. So we have to get dp of jth value plus 1 if this value is greater than our dp ith value. So this is here I. So what we are checking, if we are adding 1 to our previous value, and that means we are adding this to our subsequence, that is we are making a subsequence of 1 3. So we are considering this subsequence, that means the previous subsequence of 1, that is here only 1 length, and we are adding 3 to that subsequence, that means we are creating this subsequence 1 and 3, and that means adding this previous subsequence to our 3 will have a greater size. So if we have a greater size, that means this is our smaller value and this new value is our greater one. So we will just update the value of 3. That means dp of I will be equal to this, dp of j plus 1. And after that, we will also check our maximum size. So we will just check, right? And that is it. That is the only condition we have to check every time. So, and after that, we will just check again this thing. So we will just check with 2. So after checking with 1, we will check with 2. So either the subsequence, the maximum length subsequence with 2. What is the maximum length subsequence with 2? That is 1 2. And we are checking for 3. Is 3 is greater than 2, right? 3 is greater than 2. So we will add 3 to our subsequence, and that will make a length of 3, which is obviously greater than our 1. Or if we are checking with 1 and 3, then here it will be 2. And if we are checking with 1 2 3, then obviously 1 2 3 size is greater, so we will just remove it and we will increase the size to 3. And after that, we will check with 1. So we will check 1 with this, with this, with this, and this. So 1 is not greater than, so the maximum answer for 1 is here 1. And when we are checking with 5, so we will check 5 with 9 with 1. So when we are checking with 1, then we are checking for a subsequence 1 5. So it will here have size 2. And when we are checking with 2, we are checking for 1 to 5 subsequence, and then it will have size 3. And when we are checking with 3, so I is here and j is here. So we are checking for 1 3 2 3 5. So we are checking for this subsequence, and this subsequence obviously have greater length than our current one. So we will just update the answer to 4, and you can see the 4 is our maximum answer that we have to return. No, 4 is our maximum answer for our longest increasing subsequence, and we have to return n minus longest increasing subsequence, because we have to find the minimum number of students to be removed, right? So we will just do this LIS problem, and that is the only formula we have to use here. So we will just use here two loops. First of all, we have to create our DP. That DP will have n length, and we'll just write here n. And we have to fill that DP with all the 1 values, because initially all the values will be having maximum length of 1 for their maximum length increasing subsequence. So we will just fill that DP arrays dot fill with 1. And after that, we have to traverse in our DP from first value, because we cannot just check for 9, right? What we are doing every time. So let me clear it. Every time what we are doing, we are having some is pointer, and we are checking all the values previous to that. So we cannot start from 9 because there is no previous value. So we will just start from our first point, first index. So I should be less than n, and we will just have our j loop. So j will be equal to I minus 1, and or we can start from 0. So that is totally your choice, and j should be less than I, and j plus plus. So that is the thing we are doing here. So we are having some I here and we are starting from 0. That first of all this particular subsequence and after that this. So they will be increasing every time and they should be less than. That means we have to check up to this here. Only up to this when we have subsequence length equal to 2. So what we have to check? We have to apply this condition that if our jth value, that means height of j, is less than height of I, or we can say when ith value is height, that means ith person height is greater than jth person height. That means first of all there is some smaller person and there is some ith person that have some greater height. So we can just consider it as a new subsequence and we have to check also this condition here that either this is including in our maximum answer or not. So we also have to check this condition. This condition is a must because suppose we have some another example 1 and 4 and 2 3 5. So what is the maximum value for our 5? So if we are checking for 5, so first of all we will check with 1 the maximum subsequence for so we have to create here a dp. So first we will create first of all answer for 5 is 1 and for 1 it is 1 here, for 4 it is 2, that is 1 or 4 subsequence. And when we are checking for 2 there is also length 2 because the maximum subsequence in this range will be equal to 1 2, that is maximum increasing subsequence, right? And when we are checking for 3 the answer will be 3 because the maximum increasing subsequence for this range will be 1 2 3. So I hope now you are getting this. So this is the dp array of our this example. And when we are checking for 5, so that means when I is equal to here, so when I is here we will check every value. First of all we will check this value, then that means we are checking for 1 or 5 subsequence and that will increase our answer to 2 because this have answer 1 plus 1 will be equal to 2, so we are updating it. And when we are checking for 4, so when we are checking for 4, so this is here that have answer 2, that means the subsequence is 1 4 and we are adding to 5, so 2 plus 1 equal to 3, so we will update our answer. So that means when we are checking here for 2, so suppose 3 is not here. Okay, just take some another example. That example is straightforward. So let me just complete it. So when we are checking for 2, the subsequence is here 1 2 and we are just appending 5 here. So 1 to 5 that also have answer of 3. So we will just append it to 3. So we here the answer is current answer is 3 and the answer we are getting with this subsequence 1 to 5 is also 3. So we cannot just update it. We have to update only when we are getting a greater answer. So like in this case when we are checking for this example 1 2 3 5. So when we are checking for this subsequence 1 2 3 5, so that means our length is 4, maximum increasing subsequence length is 4, so we will update it. So that means if dp of j plus 1 is greater than dp of I, then we will update this dp of I, that means our maximum increasing subsequence for our ith value dp of j plus 1. And we will also have some answer, that is math dot max of answer and dp of I. So we will just create that answer that will be equal to 0 because the minimum length is obviously 1. So we can also initialize it with 1. So that's not a problem. And at last we have to return, but we have to return n minus answer. So that is not answer because that is our LIS, longest increasing subsequence, the maximum number of students that can be present in our assembly. So that can be answer, and but we have to return the minimum number of students that we have to remove. So that is obviously total number minus maximum student can be present. So that is our final result, and that will just give us time limit exceeded error because you can see here the time complexity is here n square and the constraint we are using here is 10 to the power 5. So that will definitely give us time limit exceeded. Okay, that is the wrong answer. When we have answer, okay, we have to initialize it with 1. So that is just a silly mistake. We will definitely have time limit exceeded because here you can see, because here 10 to the power 5 and 10 to the power, if we have constraint equal to 10 to the power 4, maximum value is 10 to the power 4, then this solution will get accepted. But here we have 10 to the power 5, that means we have to optimize it. So I will just tell you a different approach for using this LIS. So the approach will be same, that means we have to find the longest increasing subsequence, that means maximum number of students can be present in our assembly, we have to find that, but we will just do that in a different way. So how can we do it? So let me just tell you that approach. So first of all, we have this example 9 uh, 1 2 3 1 5. So this is our example, and what we will do, first of all, we will create a array list. That means this is a dynamic array. So what we will do, we will just create that, and what we will store in this array, we will just store the maximum possible length, maximum possible. We will just directly store our increasing subsequence in this. We will not store our DP. We will just store our longest increasing subsequence with all the possible minimum values. So first of all, if we have 9, so the minimum, first of all, this array is empty here. So this array is empty and we have only one value 9. So that means we will just get the position of this 9. So if the position is around this value, so that means if the position is if this value is the maximum possible for this array, that means we will just append this 9 here. So we will just add this 9 here, and after that we will get the position of this one. So after that we are checking for one. So what we have to do every time, we have to bind this up in this array list, and we have to get the position of this current element. Because what why we are doing bind this up, why we have to get the position of this element, so that is the question. So we have to get the position, because if this element is greater than all the elements in our previous range, that means we are checking in our previous range. So we are checking for any previous subsequence, right? That increasing subsequence will be present in this array, and if that value, if that ith value is greater than any previous subsequence, so that will be appended here. So that will lead to increase in the length of our array, right? So but in that case, if this value is smaller, so what we will do, we will replace any previous value which will be present here. So just like this, just like in this example, I will just tell you more examples so that you will just get comfortable with this approach. So first of all, we can just compare, we can just get the value of this one in this array. So what will we return? So after doing a bind research, the index will be returned as 0. So 0 will be the index that this value should be present on. And what we will do, we will just update this value to the 0th index that we will have after bind research. And we have to always find lower bound, because if the values are same 1 1, then we don't want two person of same height to be present in our assembly. So we also always have to find the lower bound. So I will just give you more examples so that you will get comfortable to it. So in this example, currently we have to say we will find the actual position using a binary search. So the time complexity will be log n, and we have to find it for all the values. So total time complexity will be n log n, which is optimized than n square. So we will just get the position of this one, and that will return as 0. So we will just update at 0th index, that is here 9 with 1. So that means the minimum value possible up to this range, up to this I, the minimum value possible of our increasing longest increasing subsequence will be this array. So in this array, what we are storing, you have to remember that thing. We are storing in this dynamic array, that is array list. We have to store minimum, first of all, maximum length increasing subsequence with minimum values up to some ith index. So that is the thing you have to remember. And let us see how we are storing this maximum length increasing subsequence. First of all, up to some ith index. So when we are checking for some ith index, that means when we are here, so what is the maximum length increasing subsequence with minimum values? So what is the maximum increasing length subsequence? So that is here 9. So we were just storing here 9, and after that, after we are here at I, so that will be our range. And what we have to store, maximum length increasing subsequence with minimum value. So with minimum value up to I. So when we are checking up to I, and we have to store only minimum value, so 9 or 1, which is minimum. So 1 is obviously minimum, so we are using here a bind research to find whether this value is minimum or not. So here 1 will be updated, because that is the condition we are satisfying here, maximum length increasing subsequence with minimum values. Minimum values means that this subsequence will always have minimum values, like 1 2 3. And if we have 100 here, so 100 will be not added here, this 5 will be added, because 5 is smaller than this 100. So that is the thing we are doing here, minimum value up to some ith index, or we can just say up to some ith index, we have to add it in front here, up to some ith index maximum length increasing subsequence with minimum values. So 1 will be here, and after that our range will be increased. So I will be here, and we have to check for this range now. But we have to check for this ith range maximum length increasing subsequence with minimum values. So we will just get the index of this two using a binary search. So what will be the index? So this one is smaller than this, so what the index will be returned as 1. So after doing a binary search, you can do it manually, and this will be definitely one index, right? So we will just check is this length is smaller or equal to this smaller, not smaller. We have to just check equality, right? Because this one is equal to length. So what we will do, we will just append this. So we will just append this 2 here, and that means the longest increasing subsequence up to this index with minimum value is 1 2. So that is the answer here. And after that, if we have our third value, so that means, okay, let me just erase here. So that means our range will be here. So now we have to find up to this index what is the longest increasing subsequence. So the index of 3 will be again 2. So that is the length of our array, and that means we will append this 3. So that means the longest increasing subsequence up to this index is 1 2 3. And after that, suppose here it is 1. So we have to now check for this range. So our range is increased here, and we have to check for all the values. So we will just bind the search in this array, and we will get the position of this one. So what is the position of this one? So position will be -1. I think it is -1 because we are using here lower bound, right? So if it is -1, then we just cannot do anything. So we will just remove this, right? Yeah, I think the value will be -1 because what we will do, okay, we will just do that in our algorithm. So just remember that thing, this will be -1, so we will not add this, and after that our range will increase. So our range will be up to 5, and we have to get the index of 5 now. So index of 5 will be returned as 3. So we will definitely have the index 3, and that means this is equal to length. So we will just append this value. So 5 will be here, and we will just return this length as our longest increasing subsequence, and we have to return n minus length of this array, because that will be the minimum number of students that we have to remove. So let me just implement that in algorithm in our program. So we have to create an array list that will have integers, and that will act as our DP here, because what we are storing here, we are storing the longest increasing subsequence up to this point, up to this point, up to this point. So at every point we are just storing the longest increasing subsequence with minimum value, because every time we have to store minimum value, so that even if some so even if we are even when we are storing here 300, and we have here 4 and 5. So if we are storing 1 2 and 300, then obviously there is not minimum values present here, but we can see the longest increasing subsequence is 1 2 4 5. So that's why we have to store only minimum values. So when we have 300 here, and after that we have 4, so what will be the index of 4? So index of 4 will be here 0 1 2. So we will just replace this value with 4, because the index of 4 is 2. That is some valid index in our array list. So this will act as our DP to get the minimum possible values of LIS, longest increasing subsequence. And what we will do here, so we have to traverse in our all the values first. So we will just traverse using a loop, and after that we will just get the index of this current value. So we will just get what is the index of using a binary search. So binary search of this current value, that means height of this ith value in our DP array. So that means first of all, initially this array is empty. So let me just do that again with our implemented algorithm. So initially this array is empty, and we have to get the index of this 9. So what will be the index? So index will be equal to, I think index will be 1. Yeah, index will be 1, right? So what we will do, or we can just add here 9. So that will be a little easy for us. dp dot add height of first index, first this first value, and after that we have to start crossing for our first. So 9 will be already here, and we are checking from this point. So that is totally your choice. You have to just implement your binary search like this. so that you won't get an error while when your DP array is empty. So you just have to implement your binary search and you are good to go. So when we are here and 9 is present in this array. So what we are checking, we are checking the binary search and getting the index of this one. So what will be the index of this one? That is here 0. And let me just first implement this binary search so that you can know how it is 0. So it will return as integer binary search and add a list of integer. So we will get a low value, that is here 0, and a high value, that is here 1. Okay, I think we don't have to do this because we will just return this 0. So let me just show you here dot size -1. So that is our last index, and we have to do while low is less than equal to high. And I will just show you why we are using here less than equal to. So into middle value is equal to low plus high by 2. So that is a very simple thing. I hope you know this thing. If you are doing any medium problem, you should know some basic things, right? Like this minus. So after that, we have to check if mm, get middle value is greater than or equal to our element. So even if our value is greater than equal to, then we will just reduce that value. That means we have to check before that mid -1 else, and at last we have to return low. So we don't have to add this here, and we have to start from 0. So when initially what we will do. So first of all, we are here at 9, and we are doing here a bind search, and what it will return. So 9, we are passing here 9 and this empty array. So we are passing here the element is 9 and the array's length is 0. So L equal to 0 and high value is equal to arrays dot size -1, that is 0 -1. So H will be equal to -1. So H is obviously lesser than our low value. So we will just not enter in this while block, and at last we will just return this low, and that is here 0. So this index value will have a 0, and after that we have to check if index equal to dp dot size. So that is what we were doing. If index is equal to dp dot size, so that means if it is 0, then that means this should be at the end of our list. So whatever be the list, if it is 1 2 3, and if it is returning the index of this value is equal to our size of our list, then this should be at the end of our list. That means this is the greatest element in our assembly, greatest height person is in our assembly. So what we will do, we will just add dp dot add that value at the last. So we will just add that highest person, or else what we will do. Okay, else we have to dp dot set that value. So I will just show you. First of all, we are appending in this case. So first of all, we are here and we are getting the index using this binary search, and we will just get 0. So this length is equal to 0, and length is equal to 0, and this index is also equal to 0. So that means we will just add this value to our dp array list, and 9 will be here, and after that I will be increased. So I will be here, and after that we will check the index of this one, and that will be also returned as 0, because you can just see here we will start from 0, and h will be equal to this is here 1 -1, that is 0. So low is equal to 0 and high is also equal to 0. So we will just enter here, and mid value is also equal to 0. So mid value is 0, and we'll just check if the middle value, that means on 0th index, if the value is greater. So on 0th index, if the value is greater than this element, so obviously this value is greater than this element, so height is equal to mid -1. So high is equal to mid -1, high was already 0, and if it is mid -1, so high will be equal to -1 and low is equal to 0. So we will just break out of this loop, and we will just return our low value, that means 0th index. So here index will be returned as 0, and this is not equal to our size, right? Because size is equal to 1 and we are returning here 0. So then what we have to do? we have to always store the minimum values in our DP array. So we will just remove this and we will store the minimum value here. So we just have to set on, I think we have to store here index. So I just forgot that method, that method. So that is index and then value. So correct me if I am wrong. First we have to pass the index and then the value. So we will just see if I am wrong here. And yeah, at last but we have to return n minus dp size. So that is all our algorithm, and we will just see this example. So one will be here, and let me just try run this. So after this we are at here at 2. So what will be the index return for 2? So we are here. So low is equal to 2 and high is also equal, low is equal to 0 and high will be also equal to 0 because there is only one element currently. So we will just enter here and we will just get middle value. So mid is also equal to 0 and we will just get if the middle value is greater than element. So if mid is equal to 0, so we will check this element. If this element is greater, so we can see no, this element is not greater than our 2. So we will just enter in this else block and low is equal to mid plus 1. So low is equal to 0 and mid is also equal to 0. So what we are saying, low equal to mid plus 1, that is low will be equal to 1 and high was also 0. So we can see high is greater than low is greater than high. So we will just exit of this loop and we will just return low, that is here 1. So we are returning 1 for this 2 value and that is here equal to our dp size. So we will just append this 2 here. So I hope now you are getting this, and we will just do the same for this 3, same for 5, and that is all our algorithm. And that is here, this time complexity of this loop is n, and for this binary search it is here n square. So that is it about today, everyone. If you like this video, then do subscribe to our channel and just drop a like and also drop a beautiful comment, and you will just get this solution in our DSA repository. Let me just know in the comments that you if you know this algorithm already, or if you understand a new concept today. And that is it. So let me just paste it here. Okay, it is not responding. So that is it about today, everyone. I know the video is very long, but it will be worth it if you are understanding today a new concept, that is the longest increasing subsequence. So do practice this question in on LeetCode and GFG. There is a separate question for this longest increasing subsequence, and just try this approach if you can do this by yourself. So thank you for watching, everyone.